Hello everybody.
Check if everyone is able to hear.
Are we audible to everyone?
Yeah. Yes. Yeah.
So welcome again to another session of Apache Apex. Before we start, we are thrilled to announce that the project is now a top-level project. Thanks to the entire community and the people who have made this a big success. Thank you to everybody. So again, in this session, my colleague Shubham will be covering another topic, and as normally we do, we would take some questions in between, and obviously most of them at the end of the session. So I'm handing it over now to my colleague Shubham.
Thanks, Mohit. Hello, everyone. I'm Shubham. I work as a software engineer at DataTorrent, and today we'll be talking about how to develop an application on Apex and for log ingestion. So I'll be talking about an application that we had developed for a customer, and in which we ingest logs from Kafka and push it onto HDFS so that you can query it in real time using Impala. So this is the agenda for today's session. We are going to talk about a use case. So the customer, it was in the domain of fraud analysis. So I'll give you a brief overview of what the use case was. We will then see what other technologies used in the use case. After that, we would go through some of the use case specifications, followed by the DAG design. So we'll see how the application was translated into an Apex application. And we will conclude the session by having a comparison between a batch and a streaming approach. So this application was actually a batch process initially, so it was solved using a batch approach, and we optimized it using the real-time streaming platform. So we would have a comparative analysis of batch versus streaming. So let's start. So as I mentioned earlier, the use case was for a customer who is in fraud analysis domain. So at a higher level, this is the design. So let me explain you the use case in a bit detail. So we all know that there are these e-commerce websites on which users log in and do their transactions. So all these transactions, they generate a huge amounts of data, and there is obviously a chance of fraud. So the customer for whom we develop this application, they have this data from all their other customers, which they move to Kafka, and so they wanted a querying mechanism wherein they could quickly query the data and use it for further analysis and to generate reports. So if you observe that this design is, although this was for a customer in fraud analysis domain, we can use this design for other use cases as well. For example, even in advertising domain, we have DSPs who have tie-ups with a lot of ad servers, and even they have the need to generate real-time reports. So this is a pretty generic design, I feel, which a lot of other companies in other domain can also make use of. So before we move on to the use case specification, we would talk about some of the technologies that were used in this application. So first, just a little bit about Kafka. So Kafka is a messaging system. It is fast, it's scalable, it's persistent, so you can persist the messages for a particular duration before consumption. And so basically on a higher level, it just maintains fields of messages and called as topic. It has producers. We can say these are just simple processes that publish the messages to the Kafka topic. Then we have a broker, which are servers, and which communicates between the producers and consumers. So consumers are just the processes to consume the messages from the brokers. Let's now talk about Impala. So Impala is a massively distributed, massively parallel query engine. So what we mean by this is that it runs as a distributed service on your Hadoop cluster. So you have Impala daemons on each node, and whenever we fire a query, it distributes the query across all the nodes and gives the result back to you. Impala has an SQL on. It can also be called as an SQL on top of Hadoop. So it provides users with a SQL language which they are already familiar with, so they can query it using SQL. If we all must have heard about Hive. So but Hive, generally when you query something using Hive, it translates it into several MapReduce jobs, which it's very slow. But unlike Hive, Impala does not use MapReduce underneath. It's a completely new execution engine, and hence it gives the results much faster. And it has high throughput and a low latency. So whenever we use Impala, we need to consider certain factors to get the best performance results. So I'll be talking about some of them. So one is partitioning, the other is file format, and the third is block size. So let's go one by one. So first is partitioning. So partitioning is just dividing your data set into different directories. So let me give an example. Suppose you have the data of school records, and each record will have a column which is for an year. And suppose we know that whenever we are going to query this database, we would have year in the where clause of the query. So to get the best performance, what we should ideally do is create directories for each year and put all the relevant data files for each year into those directories. So using partitioning, it speeds up the queries. The second factor which we must consider for good performance is the file format. Impala is designed to work best with the formats that are columnar. So Parquet is one such example. So even in this use case, we save the data onto HDFS in Parquet file format.
So we have a question from the audience. Salaja has a question that is it an in-memory execution model?
Impala.
Yes, Impala is an in-memory execution model. It does not translate the queries to MapReduce jobs. It has its own querying engine, and it's in memory basically.
Yeah.
Yes.
It has a cache, and it also has HDFS as a permanent store.
Are there any other questions, Mohit?
Yes, so
Could you please briefly show slide 6 again?
All right.
I saw one from Satish. Satish, do you have any question as of now, or we can take it at the end?
The question is, can you explain Parquet file format? So repeat your question.
Yes. So after this, so the question is, we want to know about Parquet file format. So yes, after this slide, we will discuss a bit about Parquet format as well. So let me continue with this. So we just spoke about how important is the file format to achieve the best results, and Parquet certainly is the recommended file format whenever you use Impala as a query engine. The third factor which we should consider is the block size. The block size defines the degree of parallelism, because whenever we query Impala, each block is can be independently processed by a core. So if you have large number of if you have a larger block size, then you would have fewer blocks, but which could reduce parallelism, but you will have a better I/O throughput. And if you have a smaller block size, you could certainly have a greater parallelism, but that could reduce the I/O throughput. So depending upon the size of the data, the input rate of the data, we can experiment between different block sizes. But for Parquet, it is recommended that to have a block size of 256 MB. Moving on to the next slide. So here, let's discuss about what is Parquet. So Parquet is a column-based storage format for Hadoop. What do we mean by column-based is that the data is stored as sections of columns rather than rows. So if your data has many columns and your use case involves working with subset of columns rather than the entire records, Parquet is optimized for that sort of a use case. Also, the another advantage of Parquet is that it limits I/O because since it's a columnar, it limits I/O by loading only those columns that need to be accessed. So generally, when we say that we want to use columnar storage, we know that our queries would be mostly, querying few columns, and that's why the column-based storage format is useful. And because each column can be accessed independently, we say that it limits I/O. Columnar storage also has another advantage, that it saves space. This is because since all the values of a column belong to a same data type, we can apply better compression mechanisms, thereby resulting in saving of space. So you might have heard about Avro. So Avro is a row-based format, whereas Parquet is a column-based format. And whenever we need to access data row-wise, then Avro is generally preferred. But in this use case, we knew that the queries would be for particular columns, and hence Parquet was the right format. So let me talk about how Parquet, something more about. Yes, is there a question?
The last question. When do we store data in Parquet? So the question is, when we store data in Parquet format, does it convert into columnar, or we have to write the splitting logic?
Right. Yeah. So the question is, when we use whenever we write data into a Parquet format, does it by itself compresses the columns, or do we have to write the logic? So the answer to the question is that we don't have to actually write any extra logic for compression. Parquet provides us with APIs which internally saves, compresses the data and then flushes onto the file. So when we discuss about the format, it would be clear. So a Parquet file is made up of different row groups. So even though we say that Parquet is columnar, but it is columnar per row group. So we have records which come to us one row at a time. So what we do is we save certain number of records in memory, then compress it, and then flush it to the file. So row group can be referred to as the maximum size that would be buffered in the memory while writing. These row groups are divided into column chunks. So by column chunk we mean that column chunk means data for one column in a row group, and column chunks can be read independently for efficient scans. So whenever we query, then each column chunk can be read independently. Column chunks are further divided into pages. Pages is the minimum size that we would need to read to access a single record. And roughly the page size can be kept in between 8 KB to 1 MB. So each Parquet file has a row group followed one after the another. Row group is made up of column chunks. Column chunks are further divided into pages, and at the end of each file we have the schema, the footer, which will have the information about how to read this particular file. So each file is independent in that sense.
Question which is asking is Parquet similar to Cassandra, and then we have a few more hands over there.
Okay, Parquet is a file format, whereas Cassandra is a database. Are there any other questions?
So it seems that Videsh probably wanted to ask a question.
Mm-hmm.
There's one more question. How is Parquet different from Avro other than the row columnar format? Any differentiation you know, or?
I don't know much details about Avro. The only thing, as I mentioned earlier, is it's a row-based format, and the use cases when we need to use Avro depends upon the queries that we are going to fire against the data. And whenever we want to access the records row-wise, then Avro is the preferred format.
Right. In Avro, basically what happens is, so the meta data about the data actually kind of goes in a schematic JSON format itself. So it's a binary. So it's more of the data transition between, let's say, two applications. So if I'm passing on data from one app to another app, so that's the usage for Avro stuff. So in that, in a dynamic way, I can actually change the schema at any point in time. So that's how it benefits. So it's not a data store as such. So the comparison between Cassandra or Parquet or Cassandra or Avro is not really a comparison as such.
All right. So let's go through some of the specifications of this use case. So in this use case, as I mentioned, we collect the data from a lot of e-commerce websites. So we had events coming in from 5,000 such customers, and this data was accessed through Kafka. So, and each record was a JSON record. The maximum size of each record was 10 KB. Each record had 700 columns, and the average data inflow was of the rate 5,000 records per second, which approximates to 4 TB of data per day. So 4 TB of data per day is the data which is ingested into the application.
We have a hand from Mr. Videsh. Hi Videsh, do you have any specific question?
That's on your phone.
Hello. Hello. Hello, Anil. Can you hear me?
Yes, Videsh.
Yes, thank you. Regarding column chunks, which you were explaining in the previous slide, is there any memory range for that, for column chunks?
Column with this, so there is a memory range for row group. And column chunk is the manner in which, so column chunk just represents the data for each column in a row group. So basically, the size of the row group can be configured. So whenever you, so in the APIs of Parquet, you have an option to configure the size of the row group, which is again recommended to be in between 50 MB to 1 GB. So once you specify that, that much data is collected in memory, and all the data for one column is represented as a column chunk. So there is no, recommended memory or a column chunk per se.
Oh, okay, sure. Now I have understood. You can proceed with your presentation. Yeah, thank you for your help. Yeah.
So let's continue on with the specifications. So there was one requirement that time taken for a record to be available to query must not exceed 3 minutes. So what we mean by that is whenever an event enters into a system, we want it to be available to query under 3 minutes. So this can be considered as an SLA. And also there was a partition scheme defined which we had to follow while writing the files. So as I had mentioned earlier, the partition scheme depends on the type of the queries that you're going to receive. So in this case, the partition scheme was something as I've shown in the picture. Each record had a field, date, time, and a customer ID, and so we had to partition it using these two fields. So at the top level, we had each directory representing a particular customer, and within the customer, we had directories for each year, and within that, we had directories for each month. So as you can see here, the first record is of 21st, the first month. So that's why all the records which has that day and belongs to customer mid-4 would go under month 01 directory. So this is what the design we had made for this application. So all the blue boxes, they represent operators in Apex terminology, whereas the arrows, those represents the stream. So overall the task was to read from Kafka and write the files to HDFS. So let me walk you through the DAG design one operator at a time. So at the start, we have a Kafka input operator which reads from multiple partition Kafka cluster. and it emits JSON as strings. So each operator in Apex has ports on which data is emitted. So for this Kafka operator emits JSON records. This is followed by a JSON parser, which reads the JSON records and converts it to POJO for downstream processing. Then we have a Parquet writer operator, which reads the POJO, and then converts, and based on the partition scheme, it writes the files to the HDFS. So at this stage, we have we have the Parquet files on the HDFS, and these are ready to query by Impala. Now the issue, one of the issue with this design was that even though we have files ready to query, under 3 minutes, but this generates a lot of small files, and we know that if we have too many small files on HDFS, the name node. So basically, too many small files are not recommended on HDFS. Also, having too many small files affects the query performance of Impala, because it has to scan through more number of files. So we had to somehow compact these files, and that's the reason then we had two other operators which are periodically compacting these files. So after the Parquet writer, we have an operator called as compact metadata emitter, which receives file metadata from Parquet writer. File metadata just has the information about the file name and its size. So the job of compact metadata emitter is to just keep all these information in memory, and whenever it reaches a specified size. So in our case, we wanted to compact these files to a size of 256 MB. So the compact metadata emitter, whenever it finds that the files can be compacted to the configured size, it sends the trigger to the next operator, which is the compact data writer operator. This operator actually does the compaction. So the compact metadata object, it has all the information about the list of small files and its sizes, and compact data writer operator just have to read all those files one at a time and compress it, and then again write it onto HDFS. So compaction is really important to improve the performance of Impala queries. Now, the design which was shown earlier could solve the problem, functionally, but there was one limitation with the design. So the limitation was that we were doing the read and the write operation on the same directories. So as we can see in this slide, on the right hand side, there's a diagram in which we can see that the file writing and the Impala queries were we were happening on the same directory. And the problem with this approach is that the Impala query performance gets affected. So to get rid of this limitation, we had to think of some design, and what we did was that we maintained two different directories. So within each partition, we maintained two different directories. one we named it as active and other we named it as passive. And so what we did was, whenever we have the records coming, we would write the files to both the directories, but at a particular time we would inform Impala that which of these two directories is the active one, and all the Impala queries would be directed towards the active directory. And whenever we receive a trigger from the compaction operator saying that the files are ready to be compacted, then we would actually move those large files to the active directory and make the other directory, I'm sorry, so we would do the compaction operation on the passive directory and then make it active. So this way we would avoid the avoid having a performance impact. So this was the the design which we ended up with. So as we can notice, as we can see that there are two pipelines. The upper one we can term it as active, and the lower one we can term it as passive. And then we have another operator which we named as Impala operator, and the job of the this operator is to inform Impala about which of the directory is active, so that whenever you query Impala, then all the queries get directed towards that particular directory. So in conclusion, let's compare the batch approach and the streaming approach. So initially this was, as I had mentioned earlier, this was done using a batch approach, and so we had this map reduce jobs which were scheduled with Uzi, and then to maintain the states we had MySQL. So it was a combination of these, and the major drawback about this approach was that even though it worked, but 80 to 85% of the code was related to the non-functional aspects of the data flow. So when we use batch approach, we have to take care about developing our own checkpoint mechanisms for recovery. Then we need to write code to handle failures. Then we have to write code to make the data flow transactional. So whereas in Apex, all these functionalities are taken care by the platform. So you don't have to worry about checkpointing or failure recovery, because a platform provides you these features. Provides the native support for these features. Another disadvantage of batch approach was that the time taken by Uzi job to initiate. So for each job, it used to take around 30 to 45 seconds, and because of the SLA, so if you spend 30 to 45 seconds to just initiate a job, you are losing a lot of time. So whenever a job is scheduled, a separate JVM was invoked, and this actually increases the overhead. Whereas in streaming approach, whenever the DAG is submitted to the platform, that's the only time initialization time that is required, and that's the only time when so once the resources are allocated, there is no additional time taken for initialization. And another advantage of using Apex was that all these operators which I mentioned in the tag are readily available in Mallar. So you have the advantage of the Mallar library, which provides ready to use operator So be it Kafka connectors or parsers or even Parquet readers are readily available in Malhar. So you can quickly develop your applications. So yes, that's all I had from my side, and these are some of the resources. You know, please subscribe to our mailing list, and you can post your questions. You can subscribe to dev at Apex, user at Apex, and post your questions uh, and contribute to Apache Apex. So thank you for everyone for your time. Hopefully you could take some learnings from this presentation. We still have time for questions. So if there are any questions, I would be happy to answer them.
So there is a question which says there are two copies, so it's a 2x memory requirement. So is there a better solution for that?
Yeah, that's a good question.
So can you repeat the question?
Yeah. So the question is that in the other design we have two separate pipelines, which would obviously have 2x memory requirement. So is there a better design? Yes, there is certainly a better design. So one approach could be to have a single operator, which you can to have a single operator writing into two different directories, or you can have a single operator which is writing to a temporary location, and you can follow it up with another operator which just copies the file to another directories. So that could certainly reduce the memory requirement.
We have a question from Sachin Janani. I'll just unmute him.
Hello. So my question was related to the small files. So instead of closing the files, maybe after getting a small chunk of data, it would be better if we have closed it after collecting a large amount of data. Maybe that can be one thing that we can improve. Or, and why we have gone with with that approach of compacting, because till your data in your passive directory is not compacted, it will not be able to, so user will not be able to query, right? Or
yeah, so there are two things. One was that the requirement that we want to be able to query the data in near real time. So as I mentioned earlier, there was a requirement that you need to be, we need to the event which are ingested into the application should be available to query as fast as possible. And for that reason, we had to flush the data into HDFS as early as possible, and that's the reason we had and the effect of this was that generation of small files. So it was because of this SLA that we had to flush the data to HDFS as fast as possible. And
it was being flushed in the passive directory, right? So even then user was not able to query it, right?
No, so if the data was flushed on both the directories, and by active and passive, what we did was when the application starts, one of the directories we named it as active and routed all the Impala queries to that directory.
Okay.
And after some time, once we have enough files to be compacted, we did this compaction operation on the passive directory, because we didn't
Okay.
want to read and we didn't want Impala to query and do the read and write operation on the same directory. And once we compact the files, then we switch the Impala to we make that directory as active,
Okay.
so that Impala don't have to query through a lot of small files. So that was the logic behind having two separate directories for each partition.
Okay. Thanks.
So there is a question, can you explain active and passive directory concept?
Yeah, sure.
Okay.
Yeah, so first let me explain why was this done. This this was done basically to avoid read and write operations happening on the same directory. So Impala is querying to a particular directory, whereas we are also doing the write operation directory. So to avoid that, we had this concept. So with this concept, we said that we would maintain two different directories under each partition. We would write, whenever we have received the data, we would write files under both these directories. But but for all the queries would be routed to only one particular directory. And after some time, when we have a lot of small files, we would want to compact them. So obviously we cannot do the compaction on the same directory on which the Impala queries are being sent. So this compaction, so the compaction process happens on the another directory. And once the compaction process is done, we then inform Impala that to route the queries to the another directory. So we swap the active and the passive directory, and then we do the same operation on the directory which was active earlier. So then we would again do the compaction logic, so that now both these directories would have some small files, and the other would be large files after compaction, and this process keeps on repeating.
So there was a question, do we support Flume, let's say, instead of Kafka, and what all can we support instead of Kafka?
Yeah, so Flume, you can so Apex does read from Flume. We have connectors that read data from Flume. So depending upon your requirement, you can certainly read from Flume. There is no particular reason why in this case we used Kafka. This was just the existing infrastructure, and we just used that. There's no particular reason why we didn't go for Flume. But certainly, if your use case has Flume, the logs are being transferred through Flume, you can very well integrate that as well.
And in addition, there are other message queues as such. So you have JMS, then RabbitMQ. So these are the operators which are available as part of the Malala library. You can please feel free to download it. So Apex is basically the platform on top of which you can build on any app as such. It's just a matter of putting the operators and connecting them.
So there's a question back here, and I'm just waiting. Yeah, Kiran, go ahead and ask your question.
Yeah, my question is that since we maintain a lot of partitions, let's say by date we have partitions. So how often do we compact? Because this is continuous ingestion, right? So you said swapping as well. I didn't get the concept of swapping, active to passive and passive to active, because the data is continuously coming. Impala does not understand, because we are just partitioning it based on the data. some kind of you know partition like customer, as you said. So when you say day, let's say today 26, so in that we are maintaining two copies. One is active, one is passive. When we fire a Impala query, how does you segregate active and passive? Because it does not understand anything.
Okay. Yeah, I got your question. So in Impala, obviously when you create partitions, you can, with the help of alter table command, you can tell Impala that which directory has those files for a particular partition, right? And the reason we have two directories was that you have files in both, but initially the queries would be sent to one, and the compaction process we can't happen on we can't have on the same directory, and that's the reason we have another directory. And periodically after we know that okay, these are the files and these have, if we combine these files we would have in our case it was 256 MB. So when we determine that okay, we have enough files to be compacted, then we do the compaction operation on the another directory. And once we have compacted it, then we send another command to Impala saying that another alter query to Impala saying that now please route all your queries to this another directory.
How often you do it? Like?
So this was based on size. So as I mentioned that we collect this information about how many files are there in each directory and what is the size of them. And whenever we know that whenever that size reaches the 256 MB, then we do the compaction, initiate the compaction process.
Because see, reason I am asking this question is, let's say per day, we are getting data from different sources, and it is continuous. Let's say it is creating 1,000 files, or it is creating 1,000 files in a day. So you could not do swapping all the time, if I'm not wrong.
Yeah, that's correct. That's correct. That's correct. So because we write every like, because we wanted the data to be available as fast as possible, we used to write frequently. So the files that were being generated were of a very small size, and the rate of in our case, the rate at which the data was coming into the system, the swapping wasn't happening very often. So it used to take almost an hour, to have those files of that particular size. So that's why it was not that every other minute we are swapping directories. So it wasn't that case. Also, yes.
In a day, you further create the directories in the on hourly basis or something?
No, we just had partitions month-wise.
Okay. Okay. Fine. So, but you will not have too many confusions on the open file, because when you are swapping it.
Yes, we would have for swapping we won't have too many files open, but yes, you pointed out correctly. If we have 5,000 customers, then at any given point we would have those many file handles open.
Thank you.
There is another question. Kevin is asking, is part of this what is just the Apex fund? Can we elaborate on that?
Yes. So for that, let me first. Okay. So in this diagram, we can see that the major components. So one is the Kafka cluster, one is the Impala engine, which is on top of a Hadoop cluster, and the middle part is what we can say is an Apex application. So Apex application is also running on Hadoop, but it just communicates with these other services. So that is the and the Apex part, and these are the operators which are in the Apex. So these are the components of the Apex application. So it's made up of operators wherein you define your processing logic, and these arrows are called as streams, which represents the data which is flowing over the flowing between these operators.
So to add to that, the entire fault tolerance part, the entire partitioning, the scalability part is given by the platform, which is Apex. So basically, it's a YARN client that is running. So the scheduling now is handed over to YARN, and the operators are just the logical part which is put on top of Apex. So any business logic can be easily put on top of Apex as such.
Is your Impala operator part of the Malar library, or is it just an Impala 2D call?
Impala operator for this currently it's not the part of the Mallar library, because the logic was very much specific. But yes, you can certainly have an operator. We will have an operator which can use and send commands to Impala. Right now we don't have it available in Mallar library.
So there is one more question. So Ms. Varan, do you have any question?
Yes. See, I'm a bit new to Apex. I'm trying to understand the value addition here. So I'm looking at your the use case slide, the fraud analysis and reporting. So what we have is we have events on Kafka, and you are populating it on Parquet, that's on HDFS. So now here you are using Apex. The same can be done with an integration framework like Camel as well. See, it has this Kafka endpoints. So what is the value addition with respect to Apex in this case? So what I could think of is you could fire a Camel route for every partition that you have on Kafka, and you can achieve a good throughput as well. So can you just explain what Apex brings onto the table here? Sorry if the question is very basic, because I'm new to Apex.
See, so what Apex basically provides you is the fault tolerance and the scalability, and the other part is it's native to Hadoop. So basically we require Hadoop.x for Apex to run. So on the scheduling part, so you can think of it Apex as a YARN client, which is basically using YARN's capabilities for the scheduling aspect of it. The fault tolerance is both, whether it's a batch process that you might be running or a real-time streaming, is what is inbuilt into the platform as such. So let's say if the application crashes at any point in time, so the checkpointing and the commit part of the data, which is something which we have covered in our previous webinar. So this is what the platform provides. So you won't even realize that the application crashed in no time it actually comes up. Then the different types of partitioning that we provide allows you to speed up a bit. So Camel can be used as such. That's a different use case as such. But what Apex provides in terms of fault tolerance and scalability, I think that's hard to know.
Okay. So the entire event ingestion logic that runs as a MapReduce job?
No.
No. So there is no MapReduce involved at all. Everything is in a streaming way. So by streaming we mean that the data is continuously flowing into the system, and whenever you receive an event, you process it and move ahead. So it's a pure streaming approach. There is no MapReduce jobs or batch jobs or scheduling involved.
So Apex is tuned towards streaming applications?
Apex is a real-time streaming platform.
Okay, so I have a slightly different question. Let's say I have a lot of events to start with. Okay, I can stream eventually, but to start with, let's say I have a lot of events. So how could I handle that with Apex? In the same case, you have your events on the web server, right? The first time you start, okay, you will have a lot of events, right? So there, how would this solution be tweaked with that?
Yeah, so this is Sandeep here. So basically, let me reiterate your question and confirm what it is. So you already have a day's worth of data already in Kafka, and when you start, you would like to start from all that data that is already there. So you are saying there is a big backlog, and how will you handle that backlog? And then onwards, because you are able to handle the current data rate, but how will you quickly process the data that is already there, right? Is that what you want to?
Yes, yes, yes.
Yeah. So now here there's a very good feature in Apex which is auto scaling. Basically, when we partition, or let's say in this case we have Kafka connector that is connecting to the Kafka servers, you can specify rules which will auto partition it. So in this case, when it is lagging behind or there is a lot of data that is already there, you can say that, okay, right now I would like to have 16 Kafka partitions to read from the Kafka server. So these partitions will be the Apex operator partitions or instances of Kafka operator. So now your parallelism, let's say, will be 16. Once you read through all that backlog and you are back to the normal speed, you can reduce to, let's say, the partitioning of 4. And all this is seamless, and you don't have to do it manually. You don't have to do anything. This can be configured with some simple rules within the application. So something
okay,
like
if I understand it right, you're proposing to create more number of partitions.
Yes, yes. So in case the lag is big, the easiest option and the best option would be to increase your parallelism, suck in all the data, and once you are done, come down to whatever is the right number, let's say 4 or 2, whatever is the right thing. And Apex can do that for you naturally. So let's say there is some, it's typically called the lunch test. You go for lunch and there is some failure. Then you come back and restart. There is a backlog, or let's say 1 hour. How will you handle that? So it will be automatically triggering higher parallelism, sucking everything process, and once you are back, it's the normal parallelism.
Okay, that makes sense. That's one way to handle it. Okay, thank you.
Actually, dynamic partitioning in Apex.
Yep, thanks.
Yeah, thanks. So there is a question by Mr. Petiwala. I have unmuted you. Can you go ahead and ask the question?
Hello, do we have further questions?
Hello, can you hear me?
Yes, please go ahead.
Yeah, so what is our example use case for this Apex, which you have seen in practical environment? I just joined in, so I just wanted to see that.
So one of the clear case, if you look at the financials or the services side, so somebody is doing particular stock for that matter, or particular company for that matter. So if you just, let's say you want to do a basic application or just see the changes that are happening throughout that particular stock over a period of time. So you can just say, if you just want to do it over a peak time as well, on the days. So this is a clear-cut case for Apex. So you have something like, so you can think of Kafka as just publishing record by record, as and when this minor change happens to the place.
Use somewhere.
Sorry?
In production?
Yes, I think on the advertising side, we have sell-side platforms that are using, so they don't want to have stale data for their platform where they are selling basically windows of their customers as such. So that is where they want real-time data over the platform as such. That is one case. If you look at on the social media analytics side, as and when somebody is tweeting, as and when somebody is writing on Facebook or other sites as such, they have to be processed as quickly as possible for the analytics part to take over. So if you are doing anything based on an LP or sentiment analysis as such, for example. So that is one of the cases. Let's say a product is launched in the market, so it could be a manufacturing entity. And if you just want to know, so you just launch something, you just want to analyze how people are reacting to that particular product. That's a very good use case for sales and marketing.
No, but is it currently deployed in production?
Yeah,
Yes,
yeah.
yes.
So we have a number of customers who are actually using this in production right now, who are ingesting of the order of peak of 36 terabyte of data per day with an average of around 25 GB. And then there is a use case which is a well-published use case where credit card prioritization, the processing time for a tuple or a transaction from end to end within the Apex was less than 2 milliseconds. So I have actually replied that details to you in your question along with the slides.
Thank you.
So that can give you and that's an outside data torrent use case well published.
Okay.
The other part is the way you have to look at the way data is flowing. So the traditional practice is to collect the data and then do any kind of analysis or analytics on top of it. So that's a major drift in the way we look at data now.
What is the difference between this Spark streaming and this Apache Apex?
Okay, let me take this question. Can you guys hear me?
Yes.
Yeah.
What is the difference between Spark streaming?
Right. So the difference basically in Spark streaming and Apex is Apex has been designed for stream processing. Spark streaming actually sits on top of Spark, and Spark is, as you know, mostly it's in-memory MapReduce. So it's evolved from MapReduce to Spark streaming, wherein Spark streaming actually converts the incoming data into micro batches, and that actually is nothing but further into RDDs, which are handed over to Spark for processing. Right. In this case, in case of Apex, it is designed for stream processing. And when you talk about streams, it doesn't have to be necessarily real-time streams. Anything that you read, even from your data that you have stored, maybe in HDFS or database, and once you have read it, it turns into a stream. Right. It's mostly data in motion that you could think of rather than stream. So as far as Apex is concerned, what it provides you, which is different from Spark streaming, is an architecture which is designed for stream processing. Things like fault tolerance, checkpointing, automatic scaling, which are available to you out of the box, so you don't have to really write any code for that. And I know people who have written or developed applications using Spark streaming. You know how much pain it is to write all this on your own and further debug it. So I don't want to get into that. There are different use cases wherein Spark streaming is useful and Apex is useful. But what I could say is Apex is specifically designed for stream processing, whereas Spark streaming mostly I would say can be used in a much better manner as of now with relation to machine learning. Sorry. Does that answer your question?
Yeah. So the what do you call this? Apex also supports machine learning.
Yeah, it does, but it's a little bit behind Spark streaming, I would say.
So manually, we have to write rule-based stuff to do that processing.
Right. You still will have to write certain operators, as we call them, to be integrated with the machine learning related stuff that you might use. They are not available out of the box yet.
Okay, thank you.
Now,
Yeah.
Oh, go ahead.
yeah, see, we have a Storm, right? Storm is specifically meant for streaming. So how does that compare with Apex?
So the basic comparison is in terms of the type of latency that you would see. Uh, Storm also requires multiple other things wherein that basically includes more and more points of failures. I don't want to get into technical details right now, but
Okay.
the basic difference you would see would be with respect to the latency numbers that you would see with respect from Apex versus from Storm. So, I mean, one of the customers who we have in production, it's a very big financial credit card company. They actually evaluated all these solutions together, and Apex came out on top because Apex was able to give them fraud detection within 2 milliseconds. With Storm, there are a couple of other challenges. There are also some business side challenges with Storm. And not to mention a lot of code that you have to write, plus multiple points of failures that exist due to the external dependencies that Storm has. Whereas with Apex, it's completely a YARN native application. So once you have Hadoop 2.0 in place, I don't think you need anything more than that to be using Apex applications. All you need to do is write single-threaded Java applications, and everything else you get as a part of Apex.
Okay. Okay.
So thank you everybody. That was a fantastic session. Thanks Shubham, thanks a lot. And thank you everybody for your time and patience, and thank you for these fantastic questions. Please do visit our site on Apache and site at DataTorrent. The links are there. We've shared the slideshow that we published as well, and we'll put the video on YouTube soon. If there are no further questions, would like to end the session.
Yeah.
Thank you.
Slides are already posted
So slides are already there.
on SlideShares.
On SlideShares. Thank you all.
Thank you.